Hello and welcome back to another Calculus 3 multivariable calculus video. Today we're going to be going over a conservative vector field. So what is a conservative vector field? Well, simply speaking, it's a vector field that is the gradient of some scalar function, or it can also be termed as a gradient field. What that means is, well, we understand what a gradient is. That's the del operator, and what essentially that is it's a vector wherein the x component is the partial with respect to x, the y component is the partial with respect to y, and the z component, if there is one, that would be the partial with respect to z. So pretty much what this is saying is we're going to have that vector field f that's going to equal the del phi. We're using phi here because I guess we'll see later why I use phi, but you might see it denoted as like a little f. I find it easier to use that phi, and like I said, we'll see later on exactly why, but I mean, I guess kind of diving in, I just want us to observe something real quick. Well, perhaps unclear to us now why I'm bringing in the fundamental theorem of calculus, part 2, I guess I think it's called. Well, what does the fundamental theorem of calculus state? The fundamental theorem of calculus states that, well, if we have the integral of some function f of x dx from a to b, with some caveats, of course, like I said, there's a lot of, ifs and thens, you know what I'm saying? So some conditions need to be met here, but in general, that's going to be true. Then we're going to have that integral be equal to f of b minus f of a, right? So that's what the fundamental theorem of calculus part 2 kind of states. And interestingly enough, perhaps we don't think of it now, but one of the reasons why the fundamental theorem of calculus is so interesting is because it introduces a concept of path independence, meaning no matter what, we can have some function spanning all the way around, right? So we can have some function going up and down and up and down, and as long as we go from the endpoint subtracted by the starting point, well, that's going to be equal to that integral, right? So that kind of introduces path independence, and why I bring that in, well, now we're going to be introducing something called the fundamental theorem of line integrals. And I'll talk a little bit more about what that is, but just like basic calculus, so just like the fundamental theorem of calculus, we can essentially find the value of a line integral by simply subtracting the potential function, which is going to be this phi, from the potential at the end, right? So what we're doing is it's similar to the fundamental theorem of calculus. So I guess just kind of write it down here. Well, we're going to have the integral of the gradient of phi, or our vector field, dr, from a to b, and using the fundamental theorem of line integrals, we're going to be able to essentially say that it's going to equal to phi of our parameterized at b minus our phi of parameterized at a. So similarly to the fundamental theorem of calculus, this is path independent as well, meaning, well, what does that mean? That means that just like prior in the fundamental theorem of calculus part 2, well, it doesn't matter what happens in between. Obviously, it sort of matters because, there's some conditions that need to be met, as I said prior, but essentially we're going to be taking that endpoint, subtracting it from the starting point of our potential function, and that's going to be what the integral is equal to. So I just kind of want to point something out as well, because it could very well be deemed as, well, where does this coming from? Why am I just getting thrown this equation or this fundamental theorem without any proof, right? Well, okay, let's just go ahead and do some algebra here to kind of prove exactly why this works. Well, we can kind of say that this del phi dr expanded, we know that that's going to be del phi times r prime of t dt, right? Well, if we expand this further, well, we know that del phi is going to be the gradient multiplied by phi, so that's going to be the partial of phi with respect to x, the partial of phi with respect to y, partial of phi with respect to z, and that's going to be dotted with this r of t. Well, what is this r of t, r prime of t, I suppose? What is that comprised of? Well, that's comprised of some x of t, y of t, z of t component, and each of those had derivatives taken from them. So I pretty much just expanded this, and I'm going to keep expanding these until we get to a point where it's cohesive, and it's, well, why is the fundamental theorem of line integrals the way it is? It's going to prove it. Well, if we're taking the dot product here, we're going to be multiplying the x components of each and adding it by the y components and then adding it by the z components. So we're going to have the partial of phi with respect to x times x prime of t and so forth for each of these kind of terms, right? Well, what can this be written as? This can be written as, we're going to be taking the partial of x with respect to phi, multiplying it by the partial of x of t with respect to t, and adding it all the way around. And what this kind of looks like, this is a video that I made a while back, and honestly it hasn't really come up too often since then, but we're going to be using the chain rule here, interestingly enough, in order to prove that, well, this works. So taking the chain rule, it's going to simplify to taking the derivative of phi of r of t with respect to t. And this is kind of done by making one of those little tree diagrams there, where we have phi at the top of our tree, and then we have x or y or z, and then those have sub-branches wherein it's t. So then how are we going to take the derivative of phi with respect to t? Well, we're going to have to convert it to each of its little subsections, and perhaps I should have drawn it, but essentially that's what it comes out to. If we simplify it enough, that's what it comes out to. And what would happen is if we took an integral there from that a to b dt with this in the integrand, then it would be the antiderivative of this, right? So what that means is when we integrate this, it's just going to be the antiderivative, meaning if we can somehow find this phi, this potential function it's called, then we're going to be able to use this fundamental theorem of line integrals. So like I said, given some boundaries, like, we're going to have to be given a vector field f and a scalar function phi, also called a potential function, such that our f is equal to the del of phi, or the gradient of phi, and we are going to have a parameterized path in the domain of phi. So just kind of a couple of conditions there need to be met, but how are we going to be doing this? Well, there's going to be two primary steps, and I guess a third when we're asked to evaluate. Well, first of all, we need to figure out whether or not the vector field is conservative to be able to use the fundamental theorem of line integrals, right? How we're going to do this is we're going to take the curl of our vector field. If the curl of our vector field, which is equal to the gradient across our vector field, is equal to 0 in 2 dimensions, or the 0 vector in 3 dimensions, then we're going to know that it's a conservative vector field. And I'll get more into some practice on that in a little bit. But that's going to be the first condition, is verifying that it is a conservative vector field. Once we verify that it is a conservative vector field, then we're going to be taking integrals. We're going to go into more depth soon, but essentially what we're going to be doing is we're going to be taking integrals with respect to x, y, and z respectively, and we're going to be taking all of those integrals together to make a potential function. And once that potential function is made, well, all we have to do is plug in that r of b and r of a, and we're going to be able to solve our fundamental theorem of line integrals, or our line integral that we're given, of that conservative vector field. And that's going to make our job a whole lot easier instead of going through that 4-step process that I was kind of talking about in the last video. So that is the fundamental theorem of line integrals. That's pretty much what the conservative vector field is important for. Just like I said, reiterating, curl of f has to be 0, or the 0 vector, for it to be conservative. Then we're going to be taking integrals, which I will get into more depth soon, and then we are going to be evaluating at the endpoint and the beginning point. So I guess let's just go ahead and get into some examples of how to check if it's conservative. Really fast, actually. It kind of bugs me that I didn't show the chain rule for this, so it could be displayed as, I don't know, I'm just kind of yapping just to yap. But, when we're actually doing this, so I'm just going to prove it really fast. Well, in order to get this phi, so if we're taking d dt of this phi, well, we're going to have to go through the routes, right? So if we're doing our x, we're going to have to do our y, and we're going to have to do our z paths, kind of. So this is going to be the partial with respect to x of phi, and this is going to be the partial with respect to t, or not the partial, just the derivative of x of t. It's going to be a function of t, and then it's going to be you know, so on and so forth for all of these. But as you can see, the chain rule kind of states here, well, d dx of phi times d dt of x of t, well, that's going to be exactly what I wrote here. So on and so forth. This is pretty much just using the chain rule, right? So that is the proof for it. And like I said, we kind of get the point on how to do the y and the z, since this phi is a function in x, y, and z. But the point is, using the chain rule, that's how I drove that, and that is how we are going to kind of prove that the fundamental theorem of line integrals works. So now we'll get into the conservative vector field practice. So now we're going to do some check practice for conservative vector fields. So we're given a vector field here, x and y. So how are we going to know if it's conservative? Well, recall that the curl of f, which is equal to the cross product of our gradient and our vector field, that's going to have to equal 0, and it actually will equal, well, not will equal 0, but since this is two-dimensional, there's only two, this is going to be scalar. But, you know, when we get into 3 dimensions, which is going to be one of the check practices I made later on, then it'll be a 0 vector. So how are we going to do this? Well, we're going to go ahead and take the determinant of our gradient across f. That's how we're going to check the curl. If we need a refresher on how to check curl, well, we can go ahead and watch my video that I made a couple videos ago, I guess, wherein I talk about curl and divergence. So we're going to have our d dx and our d dy, and our bottom is going to be xy, and we're making a determinant here. So we're going to multiply these points right here and then subtract it with these two right here. So we're going to have d dx of y minus d dy of x. And remember that if we are integrating with respect to x of y, well, that y is just going to be treated as a constant, therefore that one's going to be equal to 0. And then similarly, we're trying to take the partial of x with respect to y, then that x is treated as a constant, therefore that is also going to be 0. So this is 0, meaning, well, this vector field right here, this is going to be conservative. Moving on to our next example here. Let me get rid of this. We just checked it. Now we're going to have our vector field is equal to negative yx. Once again, our check here is if the curl of f is equal to 0. How we're going to do curl of f is going to be the gradient across our vector field. Similarly, we're going to have d dx, d dy, negative yx, make a determinant here. We're going to multiply these two, subtract it with these two multiplied. So we're going to have d dx of x minus d dy of negative y. Well, the partial of x with respect to x is going to equal 1. And then the partial of negative y with respect to y is going to equal negative 1. Therefore, the curl here is going to equal to 2. Therefore, since, you know, it's not equal to 0, this is not conservative. Let's go ahead and do one last check here. Some practice. With curl, I guess we're pretty much just practicing. Did not close my bracket. We're pretty much just practicing with our curl here. Well, for this three-dimensional, we're going to need a 0 vector. Similar process. we're going to need a zero vector for this to be conservative. So let's just go ahead and make our determinant. Well, I'm actually going to write my f first so that I can kind of space my determinant and my partials correctly. Okay, now I'll write them. There's a determinant there. Gotta have an I, J, and K up top, of course. Alrighty, so let's just go ahead and compute this. Well, our I like to compute my determinants vertically, by the way. So I guess if you're following along with the video, you can go ahead and compute the determinant however you might want. Well, we're gonna have the partial of y e to the z with respect to y minus our partial of z, or our partial of x e to the y plus e to the z with respect to z. We're going to subtract that from our j component. Our j component, and we're going to be ignoring this in there, we're going to have d dx y e to the z, so we're going to have the partial of y e to the z with respect to x minus the partial of e to the y with respect to z. Let me move this out of the way a little bit. Now we're going to be adding our k component, which is going to be the partial of x with, the partial of x e to the y plus e to the z with respect to x minus the partial of e to the y with respect to y. So just computing these determinants in a different color, I guess. Well, our I component, well, the partial of y e to the z with respect to y, we're pretty much just going to cancel out that y and add a 1. So this is going to be e to the z minus the partial of x e to the y plus e to the z with respect to z. There's no z in this x e to the y component, therefore it is 0. It's treated as a constant. And the derivative of e to the z with respect to z is going to be e to the z. For our j component, taking the partial of y e to the z with respect to x, there's no x in there, therefore that's going to be 0. It's treated as a constant. And similarly, the partial of e to the y with respect to z, there's no z component, therefore e to the y is treated as a constant again. That's going to be 0. And then our k component, we're going to have the partial of x e to the y plus e to the z with respect to x. Well, our first component, this x is pretty much just going to cancel out and turn into a 1. So this is going to turn to e to the y plus, and then this e to the z doesn't have an x component in it, therefore it's treated as a constant. So therefore it's going to be 0. And then we're subtracting our partial of e to the y with respect to y. Well, that's just going to be e to the y. So just kind of doing our algebra here, e to the z minus e to the z is equal to 0. 0 minus 0 is equal to 0. E to the y minus e to the y is equal to 0. Therefore, the curl of f is equal to the 0 vector, meaning this is indeed conservative. So those were a couple of practices here when we were doing our conservative check. Like I said, if you need more help, go ahead and do some example problems, and maybe if you need a refresher, go ahead and watch that divergence and curl video. So yeah, let's just go ahead and get into an example, I think. Or not an example. We'll explain what the integral part is now, yeah. So we talked about how to find whether or not a vector field is conservative or not, so we did some practice there. So let's just go ahead and talk about the next component. Well, this is finding phi. Well, first of all, if our vector field is conservative, then our vector field is equal to the gradient of phi for some potential function phi. Phi is called the potential function. In other words, we're going to have this vector field be broken up into its individual x, y, and z components, or f, g, and h, and that is going to be set equal to the gradient of phi. Phi sub x, phi sub y, and phi sub z. And in case we're not familiar with the notation, these are just equal to the partials, right? So this is essentially the partial of phi with respect to x, the partial of phi with respect to y, and the partial of phi with respect to z. So it's essentially a three-step process for finding our potential function. First of all, we're going to start off by making a table here. This table is going to have 3 components if it's 3 dimensions, and 2 components if it's 2 dimensions, of course. But for this example, I'll be doing 3 dimensions. So we're essentially going to be setting our x, y, and z components for our respective vector field and the gradient of phi equal to each other. So we can observe that our x component of our vector field is equal to lowercase f, and our x component of our gradient of phi is equal to phi sub x. Therefore, we just set them equal to each other, and we're going to be doing that across the board. So we're going to have our y component of our vector field and the y component of our gradient of phi equal to each other here, and exact same for our z component. So that's step 1. And then step 2 here, well, we're going to be integrating this phi sub x, phi sub y, and phi sub z with their own respective components. So since this is the x component of our vectors, we're going to be integrating in x. Similarly, since this is our y component of our vectors, we're going to be integrating in y. And our z component, we are going to be integrating in z. When this happens, we're going to be combining the terms, because when we do this, there's going to be some similarities that pop out. So what I mean by that is, when integrating in x with respect to our integrand, I apologize, being our phi sub x, that might turn out to be a similar term in our phi sub z integrating in z. And like I said, I'll get more into that when we do an example. But we're going to be combining the terms, and we're going to be omitting duplicates. So that's kind of what that step was. So it's a 3-step process, and once we do that, we'll have our potential function phi. And like I said, what we can do with that is we can essentially use our fundamental theorem of line integrals to simplify our work quite a bit. So let's just go ahead and get into an example on how to find phi. Our example here is our vector field x, y is conservative. We proved that above. We're going to go ahead and find the potential function phi. So go ahead and following our 3-step process. Well, step 1 is going to be setting our values kind of equal to each other here. So we're going to have f is equal to phi sub x, making another little row there. We're going to have g is equal to phi sub y. And there's actually not going to be a third component, since this is 2-dimensionally. Well, this is actually equal to f is equal to, well, our phi sub x, meaning our x. This is our phi sub x, or our partial of phi with respect to x, and our partial of phi with respect to y is going to be that y. So it looks good. Now we're going to go ahead and do our second step over here, which is we're going to be integrating in their own respective terms here. So our x component, we're going to be integrating with respect to x. So let's just go ahead and integrate our x dx. Similarly, we're going to have y dy. And our final step, we're just going to solve the integration here. Well, we're going to have 1/2 x squared, and we're going to have 1/2 y squared. So our potential function, well, that's just going to be f plus g plus h, roughly. So when combining this, well, we're going to have 1/2 x squared plus 1/2 y squared plus, and then, you know, this z component doesn't really matter, right? And this can just be simplified as 1/2 x squared plus y squared. And that is our potential function phi. So a couple of notes here. If we're asking, where is the constant of integration c, and I guess I'll talk about that more in the next example, but it's there. It's kind of there, right? So, I mean, I guess I'll talk about it more, but basically it doesn't really matter. So let's just go ahead and get into another example where I explain that. So the next example here, like I said earlier, we're just going to be using vector fields that we already found were conservative. So the example is given. Our vector field is equal to e to the y, x e to the y plus e to the z, and y e to the z. That is conservative, so we're asked to find the potential function phi. Go ahead and follow our three-step process here. Our f is going to equal e to the y. Our g is going to equal x e to the y plus e to the z. And our h is going to equal y e to the z. Second step here, we're going to be integrating with respect to each of our individual components. Our x component is going to be e to the y dx. This is going to be x e to the y plus e to the z dy. And this is going to be y e to the z dz. So solving all these integrals, our potential function, well, let's go ahead and solve that here. Well, the integral of this is going to be x e to the y. The integral of x e to the y dy is going to be x e to the y. And then e to the z dy is going to be y e to the z. And then this is just going to be y e to the z. That y is treated as constant. So, first of all, I just want to talk about, well, our potential function phi, then, well, we see, I guess that's kind of what I was talking about here, is omitting duplicates. What this means is we're going to have similar terms whenever we're integrating here, right? So we actually have two terms, essentially, so we're only going to use one of each term, right? So we're going to have our potential function be x e to the y plus y e to the z. So we're omitting those duplicates. We're taking one of the duplicates, we're putting it into our potential function, and that's what it's equal to. So I guess the question now is, well, I talked about this earlier. What is the constant of integration here? Very technically speaking, when we're integrating, each of these has a constant of integration, right? So this would be, we're integrating with respect to x, therefore it would technically be a function of y and z. Intuitively, we kind of understand why this is, because if we're taking the partial derivative of whatever this function right here would be with respect to x, well, if we have a function in y and z, it's just going to go to 0. It's not going to be anything. It's going to be treated as a constant. So each of these is essentially going to have their own little functions, possible functions, the constants of integration of the variables that weren't integrated in or taken partials in. And that's essentially going to be our constants of integration, but what we're doing is integrating all three of these, x, y, and z, so our f, g, and h. We're integrating each separate part of our potential functions. Therefore, the constant of integration essentially gets picked up in the other ones, right? So the constant of integration for perhaps the x e to the y, well, that might have been y e to the z, right? Because if we're taking the partial of y e to the z with respect to x, well, that's just going to be 0. Overcomplicating it perhaps, but essentially what I'm saying is the constant of integration doesn't technically matter here, and if we did want to, we would just write like a plus c there, but it technically doesn't really matter, because any constant of integration that there might have been, any function that there might have been in different variables other than the one that we took a partial in originally for our del phi, well, it's going to be picked up by the other integrands. It's going to be picked up in the integration of our f, g, and h component. respectively. So that's essentially what the constant of integration is. If we're asking that, it gets picked up in the other integrands. So applying the fundamental theorem of line integrals here, maybe a spoiler alert, example is given the vector field e to the y, x e to the y plus e to the z, y e to the z, c is the line segment from 1, 4, 3 to 0, 1, 0. Evaluate the line integral, the vector line integral given. Well, earlier we checked that this is conservative, so we already know that this is conservative. Not only is it conservative, but we found phi. We found our potential function given up there, so that's going to be x e to the y plus y e to the z, and plus c. C doesn't really matter though. So that's our potential function there. So therefore, using the fundamental theorem of line integrals, we can just go ahead and say that this c of f dr, well, that's going to equal our phi at our endpoint 0, 1, 0 minus our phi at our starting point 1, 4, 3. So I guess just kind of plugging this in, 0, 1, 0, our phi is x e to the y plus y e to the z. Therefore, we're going to have 0 e to the 1 plus 1 e to the 0 minus, plugging in 1, 4, 3 into our potential function, we're going to have 1 e to the 4 plus 4 e to the 3. That's going to be 0. That is going to equal 1. This is going to be equal e to the 4, and this is going to equal 4 e to the 3. Therefore, we're going to have our final answer will be 1 minus e to the 4 minus 4e to the 3. So as you can see, obviously I did this in a different process since I already found that it was conservative. We already found what the potential function is, therefore it made it pretty quick. But as you can see, if the vector field is conservative, this fundamental theorem of line integrals very well may make these line integrals a lot more simple, because we would have had to go through and parameterize that line segment. We would have had to plug it into our annoying vector field, if I may, and then we would have had to find the differential, and we would have had to integrate it all. And instead of doing that, we pretty much just got to skip all the steps because we know it's conservative. We found the potential function phi, and we plugged it in. And that saved a lot of time, saved a lot of lines of math, and overall, that's kind of the big application of conservative vector fields here. We're going to go ahead and do one more harder example. We're actually going to be doing that one from scratch this time. So yeah, let's go ahead and do that one. Harder example here. We're asked to evaluate the line integral of 2xy minus z squared, x squared plus 2z, and 2y minus 2xz dr. Where c is from a, -3, -2, -1, to b, 1, 2, 3. So I guess perhaps spoiler alert that this is going to be conservative since, it's obviously in the conservative vector field video, but how are we going to check? Well, I see this function and I see it could definitely be difficult here, and it doesn't look like this right here is not a line segment. You can just kind of visually see it. It kind of looks like it's going to be some kind of curve. Therefore, we're really not going to be wanting to do our typical parameterize, integrand, differential, integrate steps. So let's just go ahead and check, I guess. I already spoiled it, but let's check whether or not this is 0. So let's check, is it conservative? I'm going to check the gradient cross f here. Our individual components are 2xy minus z squared. we're going to have x squared plus 2z, and we're going to have 2y minus 2xz. Go ahead and put in our gradient now, d dx, d dy, d dz, jk. This is three-dimensional. So we're looking for the zero vector here. Let's just go ahead and solve this. The determinant is going to be d dy of 2y minus 2xz minus the partial of x squared plus 2z with respect to z. We're subtracting our j component now. J component is going to be the partial with respect to x of 2y minus 2xz minus the partial of 2xy minus z squared with respect to z. And then finally, we're adding our k component here, which is going to be the partial with respect to x of x squared plus 2z minus the partial with respect to y of 2xy minus z squared. Combining that, we're going to do some algebra here. Well, 2y minus 2xz with respect to y, that's just going to be 2. X squared plus 2z with respect to z, that's just going to be 2. That x is treated as a constant. Going down to our j component here, we're going to have 2y minus 2xz with respect to x. So that's going to be 0 right there. And then we're going to have negative 2z. And then our partial of 2xy minus z squared with respect to z. This doesn't have a term, therefore that's going to be 0, treated as a constant. This is going to be negative 2z. And finally, we're going to have the partial of x squared plus 2z with respect to x. Treated as a constant there. This is going to be 2x minus the partial of 2xy minus z squared with respect to y. That's treated as a constant there. This is going to be 2x. Doing our algebra here, 2 minus 2 is 0. Our I component is 0, therefore. Negative 2z minus negative 2z, well, that's just going to be negative 2z plus 2z. That's going to be 0 for our j component as well. And our k is 2x minus 2x, meaning it's going to be a 0 as well. So therefore, we have a 0 vector, meaning that this vector field is in fact conservative. So let's go ahead and move on to our next step. Next step here is going to be setting all of our individual aspects equal to their components. So that's going to be phi sub x is going to equal 2xy minus z squared. That is that component right here. And then our phi sub y is going to equal the y component of our vector field, x squared plus 2z. And our phi sub z is going to equal 2y minus 2xz. Going down the line here, we're going to integrate. So we're integrating 2xy minus z squared with respect to x. Integrating x squared plus 2z with respect to y. And finally, we're integrating 2y minus 2xz with respect to z. And doing these integrals real fast here, that's going to be x squared y minus xz squared. That is going to equal x squared y plus 2zy. And our final integral here is going to be 2yz minus xz squared. So those are our individual components of our potential function. So our potential function, putting it all together, I have an x squared y here. I have an x squared y here. That's a duplicate. We're only going to take one. We have x squared y. I have a negative xz squared. I have a negative xz squared over here. A duplicate. We're going to omit one again. And finally, it looks like I have this 2zy, or 2yz, I guess, depending on how you want to orient it, component. I'll do yz. So that's our potential function here. And I guess, ooh, filled up a lot of space. We're going to have to cram it into a little bit. Sorry about that. So then I'll do this part in red so that we can really enunciate it. What are we going to do now? Well, we're going to plug in our endpoints and our beginning point into our potential function. Well, we're ending at our b, which is 1, 2, 3, and we're starting at our a, negative 3, negative 2, negative 1, meaning this line integral here. So let's just go ahead and write it. C of, we'll do f dr. I'm not going to write all that down. Is going to equal the potential function at 1, 2, 3, subtracted from our potential function at negative 3, negative 2, negative 1. Plugging all this in, well, our potential function is down here. I'll just write it out. We're going to have 1 squared. Let me make sure that we know what our potential function is. We're going to have 1 squared times 2 minus 1 times 3 squared plus 2 times 2 times 3 minus negative 3 squared times negative 2 minus negative 3 times negative 1 squared plus 2 times negative 2 times negative 1. Oh, come on, fit in there. There we go. 1 times 2 is going to equal 2. Minus 1 times 3 squared, that's going to be 9. Plus 2 times 2 times 3, that's 4 times 3, that's 12. Minus negative 3 squared is 9. 9 times negative 2 is going to be negative 18. Minus negative 3 times negative 1 squared, that's going to be negative 3 times 1, that's negative 3. Negative 3 is going to be positive 3. And then plus 2 times negative 2 times negative 1. Negative 2 times negative 1 is going to be 2. So then this is just plus 2 times 2, that's going to be plus 4. Doing a lot of algebra in my head, sorry. So it looks like our final answer here is going to be 2 minus 9 is going to equal 7, negative 7. And negative 7 plus 12 is going to equal 5. Minus negative 18 plus 3 plus 4, negative 18 plus 7, that's equal to negative 11, which is going to equal 16. That is a harder example, and actually the full example of, checking whether or not the vector field given is conservative, finding the potential function if it is conservative, and then applying the fundamental theorem of line integrals at the end there. And like I said here, this is not necessarily going to be a line segment, right? So the fundamental theorem of line integrals and overall the concept of conservative vector fields is really a method to make your life easier when evaluating line integrals. If you can use it, I honestly would. You can check, to be honest. I like to check whether it's conservative almost every time. Or at least think in my head, do a couple steps in my head, and if any of them are equal to anything other than 0, obviously it's not going to be 0 vector, therefore it's not conservative, so you'd have to go through the parameterized, integrand, differential, integral steps. But overall, conservative vector fields is a pretty fundamental topic there, and it really does make some line integrals easier. And it offers a really interesting kind of proof and fundamental theorem of calculus result.